I'll recap a little bit about last time. What our principal definition there was 4.1, where we gave a definition to the Gödel L hierarchy. So let's look at that once more. So for comparison, on the left, apologies for the scratchings out, is the V hierarchy, where we start out with the empty set and we take the full power set at each stage. We take unions at limits, and V is the union of all that there is. Right? Now L is going to be potentially a proper subclass of V. It will end up being transitive and containing all the ordinals. Right? And we'll show that it's actually a model of all the axioms of ZF. But at the moment, we are defining that by using this restricted power set operation. We just look at the definable power set at each stage, going from L alpha to L alpha plus 1. So this is a much more restrictive and indeed controlled process. Because of this, actually, we will be able to get the axiom of choice and the continuum hypothesis holding in L, because we've got this control over this growth of L at these successive stages. Limits, we do what we have to do and take unions, and L is the union of everything. And it may or may not be the case that V is all of L. So in the bottom diagram here, it may be that L is a proper subclass of V here. So our task now is to look further at some of these properties of L. And we'll see that in some ways it resembles V, but in other ways, of course, it may be quite different. We looked at definition 4.2, right, which showed that the function that goes from alpha to L alpha is definite. Right? So what we'll store up from that is that for transitive ZF minus models, right, if W's got some ordinal beta that's in there, the result of this function applied to beta is also in there. So there is some set here which is L of beta. I'm trying to get it kind of drawn in this kind of funny little way here. And it is the true L of beta, because this is a definite term, and therefore it's AD, it's absolutely definite. So Y is L of beta in the sense of W if and only if Y is L of beta. I seem to put a warning down there that this is very important. Okay, so any questions about that before I continue? Okay. So we will again continue the exposition in the notes. So definition 4.3. So if a set occurs in L, it's going to occur in one of these L alphas as we grow L upwards like this. So every set that's in L, so-called constructible sets, they'll all lie in some least L alpha. Right? So there'll be a first place where it appears because we've layered L via the ordinals there. So we define the L rank. The L rank of X. And we use rho, but with a subscript L there. Right? As the least ordinal. such that X is a member of L alpha plus 1. It's the least ordinal alpha. So we go this far through the L hierarchy to see where this X appears. And where sets appear is crucial for proving that the generalized continuum hypothesis occurs in L. So we'll want to keep track of where sets are appearing. So unlike for the rank in V, the V rank, so V rank here, this was defined to be the least alpha such that X is a subset of V alpha, which of course actually equals the least alpha such that X is a member of V alpha plus 1. So I could choose either of these as alternative definitions for that there. I can't do that here, right? So we do not define the L rank of X as the least alpha such that X is a subset of L alpha, right? This is not what we do, right? This will give an entirely different outcome. We look for the least one where it's a member. Then for 4, gives some basic properties of the levels of the L hierarchy. And actually, if you look, they're exactly the same as for the V hierarchy. So we'll take some time going through proving to get some feel for the L alphas. We'll go through and do the proofs here in detail for 4.4. So we want to prove some basic facts. And one says that the hierarchy accumulates. As we go up through the ordinals, the hierarchy merely simply grows like that, accumulates in that way. Not just subset-wise, but membership-wise. Right? Yeah. Each of the L alphas is transitive. And the ordinals in L alpha are alpha, and the rank of L alpha is alpha. So according to 2, L alpha is a member of L alpha plus 1. Right? Sorry, not according to 2. This is what 4 would say is L alpha is a member of L alpha plus 1. But here we're looking at the V rank, actually. And here's what I said out loud. The ordinals of L alpha are precisely the ordinals of alpha. Because each L alpha is transitive, the union of all of the L alphas, i.e. L, is transitive. And because of 5, L contains all of the ordinals. So those follow immediately from 3 and 5. So we won't comment more about those. And the proof is by a simultaneous induction for all of these clauses on alpha. Don't have to do it like this, but it's succinct. So they're all trivial when alpha is 0. All clauses are trivial for alpha equals 0. So we assume that they hold for alpha. So we'll suppose that they're all proven for alpha, and we'll prove that they hold for alpha plus 1. And then later we'll assume that they all hold below some limit ordinal, and we show that they hold at the limit ordinal. But in general, that's kind of easy, because the limit operation is just this union. So we just go around and do them one by one. Okay, so this holds for alpha by assumption. We want it to hold for alpha plus 1. Well, all we have to do is show that, right? We know that for beta less than alpha plus 1, right? If beta is strictly less than alpha, I know L beta is contained in L alpha. That's the inductive hypothesis. Right? So actually, all we have to do is show that L alpha is a subset of L alpha plus 1. Since by the inductive hypothesis, for beta less than alpha, L beta is contained in L alpha. So we're then going to get it's contained in L alpha plus 1. So we only have that to do. Right? So pick something in here. Let x be in L alpha, and we want x to be in L alpha plus 1. Okay. So x is a member of L alpha. By the inductive hypothesis 3 here, L alpha is transitive. So x is a subset of L alpha. So by the inductive hypothesis for 3, L alpha is transitive. So x is actually a subset of L alpha. Okay. Now I want x to be in L alpha plus 1. So I have to justify that x is a definable subset of L alpha. Right? After all, this is just the definable power set of this. Everything in here is definable over this structure. So basically what we need is that x is in a collection of things definable over L alpha, because this equals L alpha plus 1. So I need a definition. Right? I need to show it's definable. And that's what the displayed formula does. X is the collection of things in L alpha, knowing that it's a subset of L alpha. And it's definable over the structure L alpha here. And now I need a formula to define it. Well, actually, it's a very simple formula. I just look at the atomic V0 is in V1 formula here. And I need, of course, to have a valuation for the free variables in the formula. V0 is allowed to vary over the y's in L alpha to see which ones make the formula true. And we're picking out, we want the things that are in X. So I just say y in X here. So I substitute y for V0 and X for V1 here. In the notes, I don't say, in the notes, I just write yx here. And it's just left to be understood we're substituting y for V0 and X for V1. But since this is the first time we're doing this, I've been more explicit here. Okay. Okay, so what things are going to make this true? I substitute X in here. The things that make this formula true are precisely the members of X. Right? So I collect together here the members of X. I've collected them all because I know that X is a subset of L alpha. So this here is in def L alpha. So we're okay. Okay, any queries? For 2, we need not subset but member, right, here. So again, it's for alpha plus 1, I just need that, right, L alpha is a member of L alpha plus 1. It suffices to show that L alpha is a member of L alpha plus 1. Right? Because we already know by 1, I mean, just to spell it out, right, that L alpha is a subset of L alpha plus 1. So any L beta in L alpha is automatically a member of L alpha plus 1. So we just need to show that L alpha is in L alpha plus 1. And this is actually an instance of an exercise. This is, oh, sorry, lemma 319.1. So third clause, you want to show that L alpha plus 1 is transitive. Well, L alpha plus 1 is a subset of the power set of L alpha. It's a collection of subsets of L alpha. So if X is a member of L alpha plus 1, then X is a subset of L alpha. But 1 already showed for alpha plus 1, this is a subset of L alpha plus 1. So I've got elements of L alpha plus 1 as subsets. So alpha plus 1 is transitive. So this is done. Okay, 4. Okay, the V rank of L alpha is precisely alpha. Okay, so a little bit trickier here. So the inductive hypothesis is for betas less than alpha, the V rank of L betas is beta, so we'll use that. So by the inductive hypothesis, rank of L alpha equals alpha. And we want this for alpha plus 1. So what have we done? We've shown by 2 that L alpha is a member of L alpha plus 1. So what does this mean? This means the rank of this is less than the rank of that. Okay. So this is an ordinal bigger than this one, i.e. alpha plus 1 is less than or equal to the rank of L alpha plus 1. So we then need to know to show this inequality in the other direction. So for this, in the other direction, note that if something is a member of L alpha plus 1, it only got there because it was a subset of L alpha, a definable subset of L alpha. So if this is a subset of this, its V rank is a subset of the is less than or equal to the V rank of this. And this is alpha by the inductive hypothesis here. And didn't quite fit on the page. The next line is saying, then, what is the rank of L alpha plus 1? This is, by definition, the sup of the ranks of x plus 1 for x a member of L alpha plus 1. So we've just calculated for x's in L alpha plus 1, they've got ranks less than or equal to alpha. So every x in here is rank less than or equal to alpha. So this is for every x less than or equal to alpha plus 1. So this supremum here is less than or equal to alpha plus 1. And that's the other inequality here. We now have this going in both directions. That finishes 4. The last one on the list is that the ordinals of L alpha are precisely alpha. We want this for alpha plus 1. So by the inductive hypothesis and 1, inductive hypothesis is saying the ordinals of alpha are all contained in L alpha. 1 is saying that's L alpha is contained in L alpha plus 1. So all we need to know is that alpha is a member of this, because then alpha plus 1 is contained in L alpha plus 1. So it suffices to show that alpha is a member of L alpha plus 1 in order to get that alpha union singleton alpha, this is what alpha plus 1 is contained in L alpha plus 1 to get the inclusion one way. The ordinals less than L alpha plus 1 are all in L alpha plus 1. Okay, so the ordinals less than alpha, they're all elements of L alpha and they're elements of L alpha plus 1. It's this last ordinal alpha that we need to get into L alpha plus 1. So again, things in here are definable over L alpha, so we need a definition for alpha. So I just write it down. So consider this. I look at the deltas in L alpha. So the delta is an ordinal. Well, this is just a collection of deltas in L alpha. So that L alpha epsilon is a model of, well, here's the formula. V0 is an ordinal. Right? So I write that formula out. You know, being an ordinal means it's transitive and well ordered by epsilon and so on. It's only got V0 as a free variable in it. So I'll let this V0 range over objects W in L alpha. Well, I've kept them as deltas because the things that make it true are ordinals. Right? I could just say it's the W's in L alpha here that make this true. So everything that's an ordinal in here, any delta that's an ordinal in L alpha is going to make this true. Okay. We know that the ordinals in L alpha are precisely alpha. So actually every delta that's a member of alpha makes this true. So this is all the ordinals less than alpha. So this actually just is alpha. Alpha being the set of its predecessors. And here's a definition of alpha over L alpha. So alpha is in L alpha plus 1. So that concludes all of those 5 clauses, right, in the successor stage, going from alpha to alpha plus 1. Now you may be relieved to hear that actually it's much easier to do the limit stages, which we still have yet to do, right? But it won't take so long. So this concludes 1 to 5 for alpha plus 1. Okay, so we now consider we've got a limit ordinal, and 1 to 5 hold for alpha's less than lambda. And we now want them to hold for lambda. Well, let's just look here at what they say. If this holds here for any alphas that are less than lambda, right, this is now kind of obvious because L lambda, recall, is the union of the previous L alphas. So this is kind of trivial for L lambda. Right? And likewise, for betas less than alpha less than lambda, L beta is a member of L alpha. Right? But L alpha is a subset of L lambda, so L beta will be in L lambda. So again, this is trivial. Right? A union of transitive sets is transitive, so L lambda will be transitive. If the ordinals of each L alpha are precisely alpha, the ordinals of this union will be precisely the union of these ordinals alpha less than lambda. So that's going to be just lambda as well. So, oh, actually, I do give some more details on that one. Right? Sorry, I was talking as if this was talking about the ordinals. I was talking as if this was 5. Right? So tick should go here. If the ordinals for L alpha, for alpha less than lambda, just to repeat, right, are precisely alpha, I take the union of the L alphas to give me L lambda, the ordinals of that union will be precisely those less than or equal to any alpha less than lambda. So the ordinals will be lambda there. It's 4 here that needs a little bit of argument. So 1 to 3 and 5 are immediate, just using that L lambda is the union of the previous things. We need to show 4, right, that lambda is the V rank of L lambda. So what is the rank of L lambda here? It's the supremum of the ranks of x's plus 1 for x in L lambda. So it's a strict sup of the ranks of x's in L lambda. Okay, so any rank of some x in L lambda, if x is in L lambda, x is in some L alpha. So its rank then is going to be less than or equal to the rank of this L alpha. So that's less than or equal to alpha by the induction hypothesis. So we're using the induction hypothesis here. So this supremum here is just going to be the supremum of the ranks here, which are all less than ordinals less than lambda here. Here. And this is just lambda, of course. So in the other direction, conversely, because all the ordinals less than lambda are in L lambda, so again, this is we're using the inductive hypothesis here. Then this is going to mean that, okay, this is a subset of this. Lambda, which is its own rank here, is less than or equal to the rank of L lambda. Right? A is a subset of B, rank of A is less than or equal to rank of B. Here. So I have it going one way and another. Right? So they're equal. So that finishes the lemma there for these properties of the L hierarchy. Okay, any queries? Okay. So 4.5 continues this investigation. Right, for any alpha and ordinal, the L rank of alpha is the rank of alpha, which is just alpha. So we've got two different notions of rank. Right? This is the V rank, where something appears in the V hierarchy. This is where it appears in the L hierarchy. So this one we know. This is not new, right? But this is saying alpha appears at stage L alpha plus 1. Right? And we've kind of already seen this, right? So I'm going to leave this as an exercise for you to go back and see where we have seen it. Right? For n less than or equal to omega, right? Ln, just for the finite levels, this is just the same as the Vn's. So at the finite levels, constructibility just coincides with taking these power set operations, as it were. Okay, so I've left these as exercises. And as is usual with something like this, do this for 2, do this by induction on n. So you've only got 0 and successor stages to deal with. So basically what one has is, of course, Ln plus 1 is what's definable over Ln. And Vn plus 1 is just the power set of Vn. So what you have to do is to say, okay, show that any subset of Vn, which ends up in here, actually is definable. So show that the power set and the definable power set are doing the same thing. So just show that any subset of Vn is definable. Show any x, which is a subset of Vn, is definable. And we can do this because x is finite. I need a formula that defines x. Well, x, you can just list its members, y1 up to yk. So write down a formula that defines x for us. Actually, if you look back at the exercises on the def function, you'll find the tool you need to do that. There's actually either an exercise or a lemma, I don't remember, that says precisely if I got a finite, any finite subset of a structure is definable over a structure. And that's exactly what's going on here. We'll do the third clause of 4.5. For all infinite alpha, cardinality of alpha is the cardinality of alpha. So note this is quite different from the V hierarchy, right? From the V alphas. This is because the cardinality of V alpha plus 1 is the cardinality of the power set of V alpha. So that's 2 to the cardinality of V alpha. So this here is something that's going to be much bigger than alpha. But the cardinality of alpha plus 1 is alpha, or cardinality of alpha. Right, so whereas the cardinality of L alpha plus 1 is the cardinality that's less than or equal to alpha, right? Cardinality of V alpha plus 1 is something very much bigger than alpha. Right? It's bigger than the cardinality of V alpha. I mean, maybe I should say here, it's bigger than the cardinality of V alpha. So the V's grow explosively by the size of the full power set at each stage. And the L's grow much more gently. Right? So we'll just see that. Okay. Suppose alpha equals omega, so proof of 3. We've seen that L omega, this is the union of the LNs, right? And this is the union of the VNs, right? Which is just V omega. So L omega is the hereditary finite sets. And so its cardinality is omega. So we have 3 when alpha is omega, right? Because omega is its own cardinality. So we have 3 for alpha equals omega. Okay, so again, an induction on alpha. We suppose it's true for alpha. And we look at the cardinality of L alpha plus 1. Cardinality of L alpha plus 1, well, that's the cardinality of the definable power set of L alpha here. And now we use lemma 319 form. That said, the definability didn't increase the cardinality of an infinite structure here. So here we're using lemma 319 form. So this is just the same as the cardinality of L alpha. So this is gentle growth. For an infinite structure, it doesn't increase the cardinality of the structure. Induction hypothesis here, and alpha plus 1 has the same cardinality as alpha. So just again to recall, perhaps just in words, why this is the case. I mean, this is the case because the number of definitions that you can run over L alpha is restricted by our language, which is countable, only countably many formulae. And this is already infinite, it's already countable. So there are only countably many formulae, and we can use as parameters for the free variables in the formulae just finite strings from L alpha. But there's only the same cardinality as the structure, many such finite strings. So not part of this proof, but just recall, right? If you're defining something over a structure Z, epsilon here, is determined by the number of finite strings into Z, which is just the cardinality of Z, and, well, which becomes the cardinality of our possible valuations, and the cardinality of the language, which is aleph 0. Right? So this cardinality of def Z here is going to be less than or equal to, well, aleph 0 times the number of possible valuations here. So this is just aleph 0 times the cardinality of Z. And if Z is infinite, it's just the cardinality of Z. Okay, so I'm recalling there this 319.4 as to why we get this equals this, or the major facts as to why that's the case. So this proves 3 for alpha's omega and for alpha plus 1 here. So we're just left with limits. Let's look at L lambda. It's the union of the things of the L alphas here. So what have I got? I've got lambda many sets here, however big lambda is, and these sets are all of size the cardinality given by these indices here. So the cardinality of lambda times, well, each of these is of size less than lambda. Since by the inductive hypothesis, this equals the cardinality of alpha, and this is less than lambda. So the cardinality of alpha is less than or equal to the cardinality of lambda. Yeah, I better just say that straight out. So the inductive hypothesis gives me this, but alpha is less than lambda, so cardinality of alpha is less than or equal to cardinality of lambda. And this, in cardinal multiplication, lambda times lambda is just lambda. Right? Cardinal lambda times cardinality of lambda is just cardinality of lambda here. And that's what we needed there for 3. So that finishes those properties there also for L. Okay, so next time in the recorded lecture, I'll be proving that all the axioms of ZF hold inside this constructible universe L.